towards the cloud. Nice. Okay, so yeah, this is our last discussion worksheet before exam 4. So our second to last exam. So we will not have discussion next week. Y'all can use that time to study because I think the exam is on Thursday. So use class time Wednesday of next week to really study what we've done in discussion so far. Last week's discussion wasn't too in-depth, but this week is a little tricky. I want to say that this is one of the hardest worksheets that we are going to do. So I definitely want y'all to review it a few times. This isn't something you can do once and then study it one more time before the exam. You're going to need to practice this. But it's also one of those things that once it clicks, it's going to click and make a lot of sense. But yeah, so I'm going to be switching back and forth between the PowerPoint and the actual worksheet. So I will be filling in the worksheet with y'all today. But before we begin, I'm just going to give y'all an overview of what we're actually looking at. So overall, we will be studying the carbon monoxide poisoning, but before we hop into that, we need to understand the curve that can show us when this is occurring. So this is our normal hemoglobin oxygen saturation curve. So this is probably new to y'all. EKGs were more familiar, things like that, but this is probably brand new to y'all. It was brand new to me. So let's go ahead and work through understanding what we're looking at before we start onto the worksheet. So there are two markers here that are really important to take note of each time you see this curve. The numbers are 100 and 40. So 100 is showing us the lungs and 40 is showing us the tissues or like the resting cells. I normally think of it as like a muscle cell because I'm an exercise physiology major, but it could be like the kidney cells or the, other cells of the body. But for this class, I'm going to use the muscle cell as an example. So each time you see a saturation curve like this, that 140 are going to be the two markers that we're going to be analyzing. So at the alveoli or the lungs, what we see is that this point right here is telling us that it is the hemoglobin is 100% saturated. So again, this is showing us the hemoglobin and oxygen percent saturation curve. And at this point right here, it's about 97%, but we can simplify it to 100% saturation, meaning that 4 out of the 4 binding sites of the hemoglobin are bound by oxygen. So we're going to look at what hemoglobin looks like in just a little bit, but for now, just know that hemoglobin is a molecule that has 4 binding sites. And in the lungs, 4 out of the 4 binding sites are bound by oxygen. So they are fully filled. So we need to deliver that oxygen via the blood, more specifically via the hemoglobin, to the tissues of the body. So we move through the blood, and once we reach the tissues, what we see is that about 75% of that hemoglobin is saturated. So about 3 of the 4 spots are still filled, but we dropped off about 25% of the oxygen to the tissues when we move from the lungs to the resting cells. So whenever we deliver, oops, I got some people in the waiting room. There we go. So whenever we move from the lungs to the tissues, we drop off about 25% of the oxygen that was bound to that hemoglobin to the tissues or the resting.
Oh, God.
All right, there we go. So again, these numbers are going to be pretty important because they will help us kind of understand the hemoglobin function and what's going on between. So this is our normal saturation curve here. So there are 2 shifts that we normally see when looking at this curve. The first one we're going to look at is our right shift. So this is showing us right shift. So let's go ahead and break it down. So whenever we have a right shift of the curve, we still start at that 100% saturation. So 4 of the 4 of those binding sites are still filled. However, between the lungs and the tissues, we're going to drop off quite a lot more oxygen. So here we dropped off about 60%, whereas on our normal saturation curve, we only dropped off about 25%. So here we dropped off quite a lot of oxygen. So that signifies a low affinity for oxygen. And I have this put into words in just a little bit. But before I get there, let's look at the right shift. So, or sorry, the left shift. So that was the right shift. With the left shift, again, we start at that 100%, but when we move from the lungs to the tissues, what we see is that we're only dropping off about 15%, so less oxygen than normal. So with this, we can take that with a right shift, the green. Hemoglobin has a decreased affinity for oxygen. And a decreased affinity for oxygen means it's going to be more willing to let go. So decreased affinity means it's not holding on as tightly. Those binding sites are not holding on to the oxygen as tightly. So it's going to let off more than it usually would. With the left shift, it has an increased affinity for O2, meaning that it's holding on more tightly. It doesn't want to drop off as much as that oxygen to the tissues, and therefore we drop off much less than we normally would. So there's 4 things that can cause this. We have carbon dioxide, body temperature, hydrogen concentration, which signifies the pH of the body, and this molecule called 2,3-DPG. So working on into this, what we see is that an increased level of carbon dioxide will cause a decreased affinity for oxygen. So if we have more carbon dioxide in the blood, our body is going to want to release more oxygen. And to do that, we decrease the affinity or the holding, the tight bond between hemoglobin and oxygen. Same with body temperature. If we have an increased body temperature, we're going to want to deliver more oxygen to the cells. So we're going to decrease that affinity or those bonds between the hemoglobin and the oxygen. If we have increased hydrogen ions in the body, like for example, when you work out and you feel the burn when you're working out, that's because hydrogen ions are accumulating in your muscles. So in your muscle cells, when hydrogen ions accumulate, that's when you feel that burn. Those hydrogen ions will be converted into lactate, and that's why you normally hear like lactic acid being the reason for that burn, but it's truly hydrogen ions because they cause a decrease in pH. So the cell becomes more acidic, aka causing that burn. So when the cell becomes more acidic, we're going to want to deliver more oxygen to clear the hydrogen ions or clear the acidity. So that would be another reason for a right shift. And then lastly, that 2,3-DPG. So 2,3-DPG, we haven't hit it yet in lecture, and we will probably tomorrow or on Tuesday. But what the basis is it's a marker for anaerobic glycolysis. So if you're familiar with glycolysis, it's an anaerobic process, meaning it does not require oxygen, but we're trying to get to an oxidative state when we're in glycolysis. So whenever we have increased levels of 2,3-DPG or increased markers for glycolysis, that would be another reason to have a right shift to try and get more oxygen to those cells. So hang on, let me get this PowerPoint pulled up on my iPad so I can switch in between. Let's see. In just a second. Where did it go? Share. Okay. There we go. Okay, awesome. So the main associations that I want you all to be able to make whenever looking at questions that go along with this are going to be affinity. You need to associate a decreased affinity with it. Let's see. Okay, there we go. Put it back in the full screen. So you're going to want to associate like decreased affinity with a decreased affinity with a more willingness to let go of oxygen. So if it's a decreased affinity, we'll let go of oxygen more easily. We'll also not have as tight bonds. So kind of affinity, how tightly the hemoglobin is holding on to the oxygen and the strength of the bond, kind of make those associations with right shift or left shift. Because Dr. Chang can ask it in a variety of ways. He could say, okay, hemoglobin is not holding on to oxygen as tightly. Would this cause a right shift or a left shift? He may ask you, an increased affinity for O2, is that a right shift or a left shift? He may say, hemoglobin is not as willing to let go of its oxygen. Would this cause a right shift or a left shift? So make sure to associate that increased affinity with the bond of the hemoglobin and the willingness to let go of oxygen, because he could ask it in those ways. I would not just know decreased or increased affinity. I would kind of understand that decreased affinity means it'll let go, the bond is not so tight, and it'll let go of oxygen more steadily or easily. Okay, cool. So that was kind of just an intro to what we're going to be looking at today. So now we'll get into our first question. So what we have here is this guy named Charles. He has this kerosene fueled space heater, which is releasing a lot of carbon monoxide into his apartment. All of a sudden, he is noticing that his vision is blurring. He feels lightheaded, disoriented, and suddenly he passes out. His friend finds him and brings him to the hospital, and there they do a blood gas analysis. So they do an arterial blood gas analysis, and that's what we have here. So they take some blood from the arteries and they will analyze the pressure of each of these gases: nitrogen, oxygen, carbon dioxide, and carbon monoxide. So with that, we can kind of use this chart to, figure out what's going on with Charles. We can take some more information. So let me go to this. Okay, cool. So before we hop into the actual questions, let's just break down the chart and understand what we're looking at. So here is our saturation curve. This is the saturation curve. That's what we are calling it. And again, you can kind of make those same associations we made with that last curve. It looks a little differently because the O2 saturation is on this side, but we still have those two markers. We have that 100 and 40. Remember, 100 signifies the lungs and 40 signifies the tissues or the resting cells. So this 2% hemoglobin carbon monoxide curve, this is our normal curve. This is our normal curve because you can see at the lungs, we are 100% saturated with oxygen. So at the lungs right here, we are about 100% saturated with oxygen. At the tissues, we're about 75%. So that shows us that normal curve that we looked at before. One thing to note about this curve is it has a sigmoidal shape. So a sigmoidal shape is the normal shape of the saturation curve. However, once we experience carbon monoxide poisoning, the curve is going to shift into this right here. And what we see is that the new max oxygen that our lungs are going to be able to take is about 50%. So before they were 100% saturated, so 4 out of those 4 binding sites of hemoglobin were bound by oxygen. However, now only 2 out of those 4 are going to be bound by oxygen, and the other 2 will be bound by carbon monoxide, CO. So you can see, and what's most importantly to see from this chart is that when we move from the lungs to the tissues, we drop off no oxygen. There is no change in the saturation between the lungs and the tissues. Therefore, our tissues are getting no oxygen, and that is really bad. That leads to cell death, suffocation, and eventually, if not treated, death. So carbon monoxide poisoning is very serious because our tissues are getting no oxygen. So what this tells us is that when we experience carbon monoxide poisoning, we have an increased affinity for O2, aka left shift. We do not want to let go of that oxygen. That increased affinity means that hemoglobin is holding on to those oxygen and carbon monoxide bonds so tightly, and it does not want to let them go. Therefore, we never let go of those oxygens, and they do not get to our tissues. So that's kind of how we can look at carbon monoxide poisoning. So let me get my worksheet out. Okay, so hopping on to question number 1. This is really simple, and I'm not going to switch to my iPad for this one just yet because it's very simple. We can just take it directly from the screen. All right, yeah, I guess I'll switch. Oh, Emma, I'm so sorry. I did not see your chat until just now. What is the 2% in the top curve again? That's just the amount of carbon monoxide at like a normal level. Yeah. Okay. Let's see, screen share. Screen mirroring. Awesome. Okay, cool. So when looking at question number 1, what we see is that we're looking for the max amount of O2 in milliliters per 100 milliliters of blood that can be carried in Charles' blood after the carbon monoxide poisoning. So this one is super simple. So this one is really simple. All we have to do is analyze the graph and see that, normally when we're looking at milliliters of blood, he can carry about 20% of oxygen in his arterial blood. However, after the accident, he now can only carry 10. So that tells us that he can carry 10 milliliters of O2 per 100 milliliters of blood. Awesome. Okay, cool. So that is number 1. That's kind of simple. You just look directly at the chart. You just match up those milliliters with the new max. All right. So now I'm going to switch back to the PowerPoint so we can break down question number 2, 3, and 4. So before and one other thing that I wanted to point out is that carbon monoxide poisoning, that shift of the curve is a downward and leftward shift. So it's a downward and leftward shift whenever we have the carbon monoxide poisoning. So this curve moves down and to the left. Okay, so real quick, let's review hemoglobin, and then we're going to review the Bohr effect before we hop into these next couple questions. So I told y'all at the beginning that hemoglobin has 4 binding sites. You can see those here. And one other thing about hemoglobin is it has 2 forms. It has a tense form and a relaxed form. What we see is that the tense form has a low affinity for oxygen, meaning that it's really hard it doesn't want oxygen to bind to it. It doesn't care for oxygen. It has a low affinity for oxygen. You can kind of use the mnemonic like affinity and affection. Like you can think, oh, it has low affection for oxygen. It doesn't really care for it. So when hemoglobin is in this tense form, it's really hard for oxygen to bind to it. But once it does, it'll move into the relaxed form. So oxygen will bind to one of the hemoglobin binding sites. And when that one oxygen binds, it moves into the relaxed form. When it's in the relaxed form, we see it has a high affinity for oxygen or high affection for oxygen. And those last three spots will be filled rapidly. So they'll be easily filled by oxygen. However, when carbon monoxide comes in, we see that hemoglobin really likes carbon monoxide. It highly prefers carbon monoxide over oxygen. And when that carbon monoxide binds, it's going to create an even higher oxygen affinity for that hemoglobin, making that hemoglobin really not want to let go of that oxygen. So it almost increases the affinity for oxygen by hemoglobin. So those oxygens are going to be bound super tightly. So that's just kind of a brief review of what we're looking at when we are talking about hemoglobin. I should have put that kind of more at the beginning, but kind of out of place, but yeah. So now we're gonna get into the Bohr effect because that's what number 2 is asking about. So you definitely don't need to memorize this equation at all. What this is showing us is the bicarbonate blood buffering system, and definitely don't memorize this. I'm just using it as a visual to kind of illustrate what's going on here. So the Bohr effect tells us that hydrogen has an effect on the hemoglobin saturation of O2. So it has an effect on, the affinity of hemoglobin for oxygen. So if you look at this equation, what we see is that when we increase the amount of carbon dioxide in the tissues, we're going to increase the amount of hydrogen being released. So more carbon dioxide, which would be caused by not getting enough oxygen, aka carbon monoxide poisoning. We're not delivering enough oxygen. We're going to accumulate hydrogen ions. When we accumulate hydrogen ions, we favor, and this is important to note, whenever we accumulate hydrogen ions, we favor the dissociation of oxygen from hemoglobin. So we favor the dissociation of oxygen from hemoglobin whenever we increase the amount of hydrogen ions. And what we see is that whenever we dissociate oxygen from hemoglobin, we begin to release more oxygen. When we release more oxygen, we have a decreased affinity for O2, which causes a right shift. So when going back to the worksheet, let's see, let me share. So when we move back to the worksheet, when we look at this question, the Bohr effect is going to cause a right shift. And I know you might be like confused because earlier I told you carbon monoxide causes a downward and leftward shift. So make sure you know that carbon monoxide poisoning itself does cause a leftward shift. The Bohr effect is a compensatory mechanism. So it's compensating for carbon monoxide poisoning, and it's trying to get us back to normal. So the Bohr effect comes, the wording of this question's kind of poor. It should say, some say that the Bohr effect compensates for carbon monoxide poisoning, not enhances. But the Bohr effect itself will cause a rightward shift. So make sure you understand that carbon monoxide poisoning causes a leftward shift, but the Bohr effect causes a rightward shift because it's trying to compensate for that left shift that carbon monoxide poisoning caused. Okay, so number 3, if the partial pressure of oxygen in the tissues is now 20 millimeters of mercury, what is the best estimate of oxygen in milliliters per 100 milliliters of blood that can be released from Charles' blood as it circulates to the systemic capillaries? So working through this question, we are now going to look at this 20 mark. We're used to looking at, Okay, so we're now looking at this 20 mark instead of the 40 mark. So we're looking as if the tissues were at 20 millimeters of mercury instead of 40. So what we're going to take from this is you need to mark that point on the curve. So you go like this, you mark it there, and then you kind of go over. So what we see is that whenever we are looking at the deliverance of oxygen at 20 millimeters of mercury to the tissues, we have about 10 millimeters of mercury of blood in the lungs initially, because that's where we start. However, once we reach the tissues, we have about 7.5. So we have that initial 10 milliliters, sorry, I said meters of mercury earlier, milliliters of O2 per 100 milliliters of blood. And then once we hit that 20 millimeters of mercury, we have about 7.5 milliliters of O2 per 100 milliliters of blood. So what we see is that when we move from the lungs to the tissues, which we are now considering as 20, which it'll always be 40 unless told else, unless, given another value. But what we see is that that difference or that release is about 2.5 milliliters of O2 per 100 milliliters of blood. So when moving from that 100, or moving from the 100% right here to the new tissue, we release about 2.5 milliliters of O2 per 100 milliliters of blood. So that is question number 3. Awesome. So question number 4. So now we're looking at the partial pressure of carbon monoxide in the blood. And we see that it's far lower than the partial pressure of oxygen. So here we're kind of analyzing the blood gas analysis. So we see that carbon monoxide is about 0.5 millimeters of mercury, whereas oxygen is 95. This indicates that the affinity of hemoglobin for carbon monoxide is much higher than the affinity for oxygen. So we're asked how many times greater is that affinity? So what we would do to solve this question is we look at those values again. Carbon monoxide is 0.5 millimeters of mercury. Oxygen is 95 millimeters of mercury. However, that hemoglobin is still picking it up. If you think about the hemoglobin being like an Uber, terrible car, but and the Uber has 4 seats, 1, 2, 3, 4. It's, even though there's way more oxygen, it's still going to pick up carbon monoxide. So to calculate this, what we do is we take 95 divided by 0.5, the values over there, and that gives us 190, telling us that hemoglobin has a 190 times higher affinity for carbon monoxide. So hemoglobin, highly prefers carbon monoxide. I don't know why. I think we'll learn that in lecture, but it just prefers carbon monoxide way more than oxygen. Even though there's way more oxygen in the blood, it's still going to pick up that carbon monoxide. All right, cool. So number 5, would you expect Charles' disorder to be accompanied by chemoreceptor-mediated hyperventilation? So before we hop into this, let's just talk about chemoreceptor. So chemoreceptors detect 3 things in our body. What they are going to detect is CO2 levels, O2 levels, and pH, aka hydrogen concentration. So one thing you may notice is that it does not detect carbon monoxide levels. Our body has no receptors for carbon monoxide or no detectors for carbon monoxide because it's not something that's supposed to be in the body. It's bad for the body. Our body was not built to withstand carbon monoxide. So once our body picks up, once those chemoreceptors pick up any abnormalities in these three things, increased carbon dioxide or decreased oxygen or decreased pH, it would normally cause us to hyperventilate. Let's say you're working out really, really hard and the hydrogen ions are increasing in your muscles and your oxygen levels are dropping because, you're holding your breath because you're working out so hard and your carbon monoxide levels are going up. Your body's natural response to that is to make you breathe a lot harder. That's why when you exercise, like run or something, you start to breathe really hard. And that's because those chemoreceptors are picking up on these three things. However, with carbon monoxide poisoning, these all remain the same. There's not much that changes. If you look at this blood gas analysis, oxygen is normally about 100 millimeters of mercury. Carbon dioxide is always about 40 to 46 millimeters of mercury in the blood. So our body's not detecting that anything is going on. So Charles' body is suffocating because he's not getting enough oxygen, but we do not start to hyperventilate because those chemoreceptors are not detecting that anything is going on. So the answer to this is no. No, he would not start to hyperventilate because our body does not have carbon monoxide detectors, and that blood gas analysis is normal. Just because he is having carbon monoxide poisoning, those other gases in the blood remain the same. Okay, cool. So number 6. Oh, do I have a question? So number 6, we are looking at Charles, what this condition, where it's occurring, and the steps of ventilation. And the answer here is C, because the main issue is occurring in the blood. Hemoglobin is transported in the blood, so that's where this is happening. So the transport of gases between the capillaries and the capillary beds and the tissues is where this problem is occurring. If you go back up to our graph, we're not giving any oxygen to our tissues, and therefore there's an issue occurring in the blood and the tissues. All right, number 7, which disorder is most similar to the carbon monoxide poisoning? So again, this is an issue that's occurring in the blood. So the disorder it's most similar to is anemia. If you've never heard of anemia before, it is a shortage of red blood cells. So a shortage of red blood cells. Red blood cells carry hemoglobin / oxygen. So the red blood cells carry hemoglobin and oxygen. So if we had a shortage of red blood cells, we wouldn't be getting enough oxygen to the tissues of our body. And that's kind of the same thing that's going on with carbon monoxide poisoning. The only difference is your body's going to detect that shortage of oxygen and cause a response. You won't feel good, you'll feel fatigued. If you try to exercise or do activity when you're anemic, you will hyperventilate because your body's going to tell you, hey, we have really low levels of oxygen. We need to bring some more in. So anemia is not a silent killer. Carbon monoxide poisoning is, because your body doesn't detect it. Anemia is detected by the body and it's rarely fatal. All you have to do is just eat some red meat or take an iron supplement or something like that to increase those red blood cells. But that's what we would characterize carbon monoxide poisoning as being most similar to. Awesome. Okay, number 8, last question for this study. What would be an appropriate treatment for carbon monoxide poisoning? So again, carbon monoxide poisoning is decreased oxygen. So the appropriate treatment would be to give high level or pure oxygen. So give high level / pure oxygen to the patient. So they go to the hospital, they get the blood gas analysis, they see carbon monoxide poisoning is occurring. So they're going to put an oxygen mask on them and administer almost pure oxygen. So we can try and clear that carbon monoxide from the blood and, begin to increase the affinity for oxygen over carbon monoxide with the hemoglobin. Okay, awesome. So that was it for this first case study. And now we are going to look at this next one. So this is looking at this molecule called hemoglobin, developed by a feminist. So go us, female power. I like the name of that, hemoglobin. I think that's pretty cool that she didn't just name it like, Dexiglobin or something. She incorporated the female in there. And what hemoglobin does is it binds multiple oxygen molecules with a high affinity such that 100% will be saturated at 50 millimeters of mercury. So overall, we just have this super high affinity for oxygen at our hemoglobin. So what we see is that at 50 millimeters of mercury, the binding affinity is normally just about 85 to 90%. If you look, let's see, you look at our normal curve, at 50 millimeters of mercury, we're right here at about 85 to 90%. However, hemoglobin would take that and make it 100%. So when knocking into question number 1, which line is representing the saturation curve of hemoglobin, that is going to be the left shifted line. This middle line is our normal line, and you know that because you look at your 2 markers, 140, 100% saturated at the lungs, and about 75% saturated at the tissues. And our hemoglobin is going to be this leftward shifted line because we have a much higher affinity. We're holding on to that oxygen a lot more tightly. So it will be the purple line or the left shift line. Okay, awesome. So what would be the benefit of hemoglobin? So if you go to an area with really low oxygen in the environment, like a super high altitude place like Mount Everest or something like that, the amount of oxygen in the environment is going to be a lot lower. Therefore, the amount of oxygen in our lungs is going to be a lot lower, and therefore the amount of oxygen delivered to the tissues will be a lot lower. So what we see is that hemoglobin begins to appear in people that are in these high altitude areas. So they can carry more O2 to their tissues. So the overall benefit is you can bind more oxygen and yeah, you can bind more oxygen. There's a higher binding affinity. At the lungs. Awesome. So that's kind of the benefit of hemoglobin. However, one thing we're going to learn when we hit this in lecture is that it's not a perfect system. There really is no perfect system when it comes to this. That's why whenever people travel to such high altitude areas, they normally have to bring oxygen tanks with them. Like if you go to Everest, you have to bring an oxygen tank or you won't survive. So it is not a perfect system. And therefore, yes, there are negative aspects. With a high binding affinity, we're going to hold on to it a lot tighter, and therefore we won't release it. It'll be more challenging to release that oxygen to the tissues. So that higher binding affinity equals a decreased release of O2 at tissues. More challenging. So you can release that O2, it's just more difficult. If any of y'all have ever gone hiking somewhere in high altitude, like if you've been to Colorado, once you get to that higher altitude on your hike, you feel a lot more fatigued, a lot more tired. You have to take a lot more breaks. You're breathing a lot harder. So hemoglobin is kicking in, so you can bind more oxygen. You're just going to have a lot more challenging of a time to deliver it to the tissues. It's going to be a lot slower. So it's not a perfect system. It can, it will, occur, but it's not perfect. That's why you need oxygen tanks if you're really going high altitude. Okay, cool. So 10, this one's quick because we have 3 more minutes. But what we see is that now we're going to look at the effect of carbon dioxide on the hemoglobin oxygen saturation curve. This should say PCO2. So what we see is that the middle line, they tell us that is our normal. So our normal is that middle line, and the other two are not normal. So question number 1 tells us that Thomas is hypercapnic, meaning that he has high levels of carbon dioxide in his blood. So hypercapnia means high levels of carbon dioxide in the blood, more specifically the plasma. And so we're going to look at what the approximate percentage of saturation at the tissues is at 40 millimeters of mercury. So what we see here is that, again, we have our 100 and our 40. And when we are hypercapnic, we are releasing less oxygen. When we have more carbon dioxide, we're releasing less oxygen. So it's going to be this red line here. And at the tissues, we're releasing about 55% of that oxygen. So the answer to A is about 55%. But one thing to note is that this is not a bad thing. This is kind of a good thing because that means we're releasing 45% of oxygen. So, on our normal curve, we are only releasing about 25%. Here we're releasing about 45%. So our body's trying to combat that carbon dioxide in the blood. So good, because we're releasing about 45% O2. And the last question is, at what partial pressure of carbon dioxide does the amount of oxygen delivered to the tissues equal about 5 milliliters per 100 milliliters of blood? So how we would work through this one is, let me erase this real quick. How we would work through this one is we would look at our initial right here at 20, and then we would move 5 milliliters of blood. So this is moving 5 milliliters down to 15, and then we work our way over. And what we see is that when we work our way over, we are at about 40 millimeters of, we're at the 40 milliliters of PCO2. So 40 millimeters of mercury. Okay, Awesome. So that is all I have for y'all today. So again, we won't have discussion next week because y'all can take that time to study for your exam. The UGTA should be having a Q&A review, so watch for an announcement from them. And yeah, I hope y'all enjoy this rainy day, and I will see y'all tomorrow or Tuesday. Bye, everyone.